All right, morning everybody. Welcome to our second lecture for PHYS1210. So we're going to be continuing to talk about particle physics today. And since we finished in a little bit of a rush yesterday due to the late start, not yesterday, Monday, just want to go over this or just kind of briefly mention this last example that we looked at. So what did we talk about? In the first lecture, we talked about these experiments where you smash particles into each other and to try and kind of break them apart and see what's inside them. And that's going to be our, that's going to be mostly what we're talking about this week is like what are the kind of fundamental bits that come out when we smash particles into, and which ones do we think are sort of indivisible in that they don't have internal structure, and which ones are maybe made of like a combination of particles. So we're going to be just talking about the particles, and we're going to be talking about the forces between them, the fundamental forces that we have in the universe. So those four forces are mentioned on this last slide here. So we're kind of familiar with gravity and probably with an electromagnetic force. You might not be familiar with the weak and strong forces. And so we focused particularly on the strong force last time. We talked about this idea of being able to describe a force as, well, where does that force come from? There are different ways you can think about that. One way is to think about there being some kind of force field, but then what is that force field really? Another way that we can consider these forces is to think about them as being mediated by an exchange of some kind of virtual particle, and that exchange is what creates the force. So this was kind of postulated as an explanation for the origin of this strong force. The strong force is what keeps the positively charged protons and the neutrons in the nucleus when the electromagnetic force would like to push them away from one another. And so then we had this idea that that there should be some kind of virtual particle, and we also know that once the protons kind of get outside the nucleus, then they will be pushed away. And so we know that this force kind of acts sort of roughly within the region of the nucleus, but probably not outside, or at least it gets much weaker outside. So these virtual particles kind of have to be created out of nowhere. At some point, there are two particles sitting there. They want to exchange one of these virtual particles to mediate this force. That's created out of nowhere. That seems to violate all sorts of fundamental laws, like conservation of energy. But when we go to very small scales, we are allowed to sort of create energy out of nowhere, so long as we only do it for a very short time. And that's the equation in the yellow box there. We don't have time to go into where that comes from. It comes from quantum mechanics. We're just kind of taking it as an equation to use. And we used that equation to estimate what the mass of this virtual particle has to be by using the fact that we know that the force acts over a length scale that's roughly the size of a nucleus. We assumed that this virtual particle might move at about the speed of light, and so that allows us, with a distance and a speed, to get a time scale. And then for the energy, we used this expression E equals mc squared, and we're going to be using that a lot today. That's the rest mass energy. It's the energy associated with the existence of a particle of mass m. And we did a bit of algebra, and we came down to this expression for what the mass of our meson should be. And I guess the other thing that I want to just emphasize again here today is just talking about the units that we're using here, because these are the units that you're going to see in the examples, and they look a bit weird. Hopefully you would be familiar with the unit of joules for energy. That's the standard kind of SI unit, right, for energy, is the joule. Now, because the masses of all these fundamental particles are so tiny, we're typically talking about energies that are quite tiny when you measure them in joules as well. And so we just use a different unit so that the numbers are not quite so, 10 to the minus large things, so that you can work in numbers that are sort of a bit closer to 1. You make a change to the units that you're using, so that instead of joules, we use a slightly weird sounding unit of energy called an electron volt. An electron volt is just defined as 1.6 times 10 to the minus 19 joules. So that allows us to convert the energy, the delta E, the mc squared, the energy of this virtual particle, from joules into electron volts. So we've got m times c squared in electron volts, and now we just divide both sides of that equation by the c squared, and that gives us a mass. And instead of this mass being a tiny, tiny, tiny number in kilograms, it's a sensible number, but in a slightly weird sounding unit. So that instead of the unit of kilograms, we're using electron volts over c squared, or in this case, it's actually mega electron volts over c squared, because it turns out to be 130 times 10 to the 6 electron volts over c squared. So we're going to, like a bunch of the examples on the problem sheet and the examples that we're going to do today are going to be using this as well, so hopefully this starts to make a bit more sense as we go through. Right, but we should get on to what we wanted to talk about in lecture 2. So we've been doing these experiments for quite a few years now, taking particles, smashing them into one another, seeing what comes out, and trying to figure out what the sort of fundamental building blocks of everything around us are. And turns out there are lots and lots and lots of these subatomic particles. And they can be categorized in various different ways. For example, we can categorize them into leptons or hadrons. We can categorize certain particles as what's called gauge particles. Those are the particles that mediate the forces. They have all sorts of weird and slightly weird sounding names. A lot of them are represented by Greek symbols here. The quote at the bottom is just supposed to give us the idea that even an expert probably doesn't really remember what all these particles are and what all their properties are, and we certainly don't expect you guys to remember what all these particles are and what their properties are. But we're typically going to be working from like tables of information. So we're going to get a table with a list of particles and their properties, and then we're going to be trying to figure out what kinds of interactions those particles might be able to have with each other by kind of understanding some basic rules about what can happen. So it's the basic rules that we want to kind of try to get our head around, and we're not trying to remember necessarily all of the details of all of these names and what all the symbols mean. But there are over 200 of these subatomic particles. And like I say, we can categorize them in various different ways. Now, when we start to look at these tables of particles, one of the things that we're going to see are antiparticles. And probably everybody's heard of antimatter, even if it's only from watching, oh God, I don't know, Spider-Man or whatever. Whichever one of the, these movies talks about antimatter weapons and stuff. So certainly you see antimatter a lot in sci-fi, but antimatter is real as well. So it was first predicted by Dirac, and then later actually observed. The first antimatter particle to be observed was the positron, which is the antiparticle of the electron. So what are antiparticles or antimatter particles? They're particles that have the same mass as the corresponding particle of kind of real matter or normal matter, but the opposite electric charge. So every particle has a corresponding antiparticle. And how do we create antimatter particles? Well, if you have enough energy, you can sort of create them out of thin air. You can convert that energy into the mass of the particle and antiparticle pair. And usually you would do that by getting a photon with a high energy and crashing it into a target, and somehow in this interaction you would create the matter and the antimatter. So long as you've got enough energy to cover the mc squared that you need for those two particles. Of course, this process can happen in the other direction. You can have a particle and antiparticle come together and annihilate with one another. If those particles disappear, then the mass has to be conserved. That's going to be, the energy has to be conserved. That's going to be one of our kind of fundamental principles. And so when those two particles collide and annihilate, we have to create energy in the form of a photon, and that photon has to have all the energy that was associated with the particle-antiparticle pair. So it all kind of sounds a bit hypothetical, but antimatter is actually useful as well. So positron emission tomography is one of the many imaging tools that's used for looking at the human body and diagnosing various issues like tumors. Right. So it's 9 o'clock in the morning. Maybe some people are just starting to try and wake themselves up for the day. If you were going to wake up for one slide today, possibly even this week, this would be the slide to wake up for. Because this is kind of the core of what we're really going to be trying to understand and do in a lot of the examples here, is basically to make sense of the interactions that are observed between particles in all of these collisions and interactions. So there are some fundamental properties that you're probably already familiar with, the idea that they can't change. So for example, we can't create or destroy energy in general, right? We can only convert it from one form to another. So we know that in any interaction between particles, the same thing has to apply. So the total energy has to be conserved in any interaction of particles. Maybe kind of slightly less familiar, but it's another one that's kind of, that you can think of from a macroscopic point of view as well. Another thing that's conserved that doesn't change is the electric charge. So the total electric charge has to stay the same in any one of these interactions as well. But when we look at what happens in these experiments, we see that there are certain interactions that do happen, and there are others that don't, even though there's no reason on the basis of, say, energy and charge conservation why they shouldn't happen. So here's one example, a proton plus a neutron. If you only need to conserve charge and energy, then you should be able to convert a proton plus a neutron into two protons and an antiproton. Because your total charge, remember the antiparticle has an opposite charge to the regular particle, so the antiproton has a charge of -1, and so the total charge before that would be 0 and the same after. So long as you've got enough energy in your proton and neutron, you should be able to in principle, create this interaction, but it's never observed. And there's a whole bunch of other examples that show that there are some sort of other kind of fundamental rules that are underlying these particle interactions that are not, that can't be understood, I guess, from those kind of macroscopic considerations of like charge and energy conservation. So then what's been postulated is that there have to be some kind of additional rules that give some kind of extra order and structure to what's happening. And so what we have here is pretty much a list of some of these other properties that we now know have to be conserved in any interaction. So one is the baryon number. So the baryon number is just, it's a property that's given to every particle. Usually it's 1 or 0. And then the total number of baryons has to be, or the total baryon number before and after an interaction has to be the same. So it's a kind of generalization of the idea of the nucleon number, which you might be familiar with. The nucleon number is 1 for neutrons and protons. Right, so then the red text is like the most important bit on the most important slide, right? So we have these quantities that we now know have to be conserved in all interactions, and we're going to be using these to kind of understand and do a bunch of examples and figure out what can happen and what can't. So electric charge and energy and momentum, those are all things that we're probably familiar with the idea of their conservation. That is, they shouldn't change in time. But we also have the baryon number, and we also have what are called lepton numbers, and there are 3 flavors of leptons, the electron, the mu, and the tau flavors, and so there are 3 different lepton numbers. Now, again, we're just going to see those. We'll look at one of these tables of properties in a second, but when we look at a table of particles, we're going to just be given a number for every particle for these things. So we don't have to remember which particles have which properties. What we have to remember is that fundamentally charge, energy, momentum, and then the baryon number and the lepton numbers are conserved. Now to kind of muddy the water slightly, there are also certain quantities that are conserved during some interactions, but not others. And in particular, there are these things called strangeness, charm, bottomness, and topness, which are conserved where we have interactions that are mediated by the strong force, but not by the weak force. So again, just to emphasize, we're not really concerned in the kind of origin of these numbers, or how the particles get those properties. We're just going to be using the properties in conservation type problems. Oh, we got a Kahoot question. Let's see if Kahoot works today. I mean, it should work today. It worked in my office. Right. You can feel free to use something silly for your name if you want to, just don't make it offensive, right? If you like anonymity. Right, anyone else still trying to join, or are we? All right, ready for the first question. Let's hope it's got answers. If baryon X decays to baryon Y, it could not at the same time emit. Which pair of particles could it not emit, given the information that we have about the lepton numbers of those particles? There. So electrons and neutrinos have a lepton number of +1. Positrons and antineutrinos have a lepton number of -1. Time for a guess. 4, 3, 2, 1. All right. Excellent. So we got 13 people went for the right answer, which is B. Baryon X decays to baryon Y. It could not at the same time emit a positron and an antineutrino. That's because the positron and the antineutrino both have a lepton number of -1. So we would be sort of adding -2 to the lepton number, which we can't do. The lepton number is one of the things that has to stay always the same. It's all right to create an electron and an antineutrino, and it's all right to create an electron and a positron, because each of those pairs has lepton number -1 plus 1, which adds to 0, so that if we create those particles in those combinations, we don't change the lepton number, which is the important thing. All right, there's the leaderboard for now. Let's come back to here for another question in a minute. Strangeness was one of the things that I mentioned in a little while ago. It's a bit of a weird name. It was, these particles were given the property of strangeness because they seem to have strangely long lifetimes, and that the lifetimes of the particles were predicted to be like 10 to the minus 23 of a second, but they were instead in this enormous number of 10 to the minus 10 of a second. These things turned out to, again, always be created in pairs. Only certain interactions were observed. So this is kind of the way that these properties have built up, and I guess maybe why some of them have slightly weird names, is that it's all kind of driven by these experiments, by seeing that certain things happen and other things don't, and then saying, well, there must be some property that's causing these things to either happen or not. But again, we do have a bunch of things that we know are always conserved: energy, charge, momentum, baryon number, and lepton numbers. Strangeness is something that is sometimes conserved. It's conserved in strong force interactions, but not in weak force. Right, here's one of these tables that I've been talking about. So we have these new conservation laws, and we're going to try and use them to figure out whether certain things can happen or not, or perhaps how much energy might come out of a certain interaction, and so on. And in order to try and figure those things out and do those examples, we're going to be using something like one of these big tables of properties. So what we see if we go across the columns is that these particles are categorized. They're categorized into some of these different categories that we mentioned before: leptons and hadrons and gauge particles. We've got the names of the particles and then the symbols. The corresponding antiparticle you're going to see is usually denoted by just having a bar over the top of the particle. So for example, proton usually gets the symbol P, and P with a bar across the top is an antiproton. The other thing, I guess, to notice here is that if there's a superscript of that's either on minus or plus or 0, that tells you what the electric charge is. So for example, the pion, we've got pi plus and pi minus and pi 0, and those have correspondingly charge of +1 in units of the electron charge, -1 in units of the electron charge, and 0. And then we see that the pi plus and the pi minus are one another's antiparticle, which is consistent with this idea that the antiparticle has the same mass but always the opposite charge to its corresponding real matter particle. Now, spin is mentioned here. Spin is a quantum mechanical property. We're not going to be dealing with spin at all here, so we can pretty much ignore that, but you might meet it later on if you do some more physics. Maybe skipping over skipping over this column just for a second, we've got B, Le, Lmu, Ltau, and S as well. These are the baryon number, those 3 lepton numbers, and the strangeness. So again, the first 4 of those are things that are conserved, and so we're often going to want to know, well, what is the baryon number or the lepton number of a lambda particle or whatever it might be. And so then what you do is you go and look for the lambda particle in your table, and you read along, and you can see what its properties are. And then coming back to this rest mass column here. So it's called rest mass because it's the mass of the particle at rest. So it's the mass that's that appears in that E equals mc squared formula. So our particle, if we take that rest mass and we multiply by c squared, then we get an energy. And so the particle has an energy just by being there, and we have to remember that energy when we're considering energy conservation. The other thing that you'll notice is that we have this weird unit for the mass. So again, the mass is not done in kilograms or even pounds and ounces or anything like that. We're given it in this mega electron volts over c squared, which you get, like we mentioned at the start, by representing the energy not in joules, but in electron volts, and then the divided by c squared is associated with that equation in the red box. So again, we're often going to want to know this rest mass, or indeed the rest mass energy, the E. And so when we do, we're just going to be using the number that we see in this table. Right, so here's one example of how we might go about using this to understand an interaction. If you did do HSC physics, then you should have heard about beta decay as being one mode of radioactive decay. So in this beta decay and radioactive decay, a neutron decays into a proton plus an electron anti-neutrino. So if we've been told that this happens at school, then presumably that it does really happen, and this is something that should happen. So now we've got to just kind of check. Let's do a sanity check and make sure that if we look at across our table, we can kind of verify that all these numbers are the same, and so everything should be all good. So how do we do this? Well, we just take each of those numbers in turn, and we've got to look at what the total baryon number is after and what it was before, and hopefully those are the same. They have to be the same in order for this to be an allowed interaction. So all we do then is we just go through and we look at the properties of all of our particles and we just add them together. So initially, for example, the baryon number, we need to know the baryon number of a neutron, so we go to neutron on our table, we go along to the column with capital B for baryon number, we see that the neutron has a baryon number of +1. So the total baryon number before the interaction is 1. Then we need to know the baryon numbers of the proton, the electron, and the electron anti-neutrino. Proton has baryon number of +1, but the electron and the electron anti-neutrino both have baryon number of 0. So that gives us a total baryon number afterwards of 1, the same as what it was before. So that's all good. The conservation of baryon number holds. So we can then do the same thing for those other quantum numbers. The lepton number, Le, would be 0 for both the electron and the proton. That's this second number here, the second column. And then it's +1 for the electron. But the electron anti-neutrino has the opposite lepton number. So it has -1. So we've got a +1 and a -1 afterwards, and the total lepton number is still 0. Similarly, electric charge of a neutron is 0, and we've got a proton and an electron with opposite charges afterwards, and so the charge is conserved. So to show that some interaction can happen, we've got to check that all of these possible rules are satisfied. Another type of example that you might be given is to show that a certain interaction can't happen. Now, in order to show that an interaction is not possible, all we have to find is one of these rules which isn't satisfied. So long as one doesn't work, then we know that the interaction can't happen. Whereas if we want to prove that something's possible, we've got to check everything and make sure everything works out. Oh, another Kahoot question. Here we go. A proton and an antiproton collide and annihilate. After the collision, what set of particles could remain? Oh, you've got to have good eyesight for this. Although you are given 60 seconds, so. Right, so we've got a proton and an antiproton coming together. What set of particles could possibly remain? We're going to be thinking about all these numbers needing to be conserved, which means they've got to be the same afterwards and before. Probably turn the music off, couldn't we? All right, so well done to those who guessed, or didn't guess, maybe knew, that it was D. It was the last answer. So none of A, B, or C. So why is it none of A, B, or C? Basically because, so we've got a proton and an antiproton. The proton has a baryon number of 1, and its antiparticle therefore has to have a baryon number of -1. And in each of the red, blue, and yellow answers, we've got a proton which has baryon number of 1, but we don't have anything in there with a baryon number of -1. And so for all of these examples, you would have a baryon number before of 0, but a baryon number afterwards of 1, which doesn't work. See how our leaderboard looks now. All right, all to play for. Got one more question coming up. Right, so we're going to go through an example where we consider conservation of energy. So we've seen an example here where we looked at the conservation of those different numbers. We're going to have to consider charge as well. Again, that's just something that you can look at numbers on a table. For energy conservation, it's kind of slightly more complicated because we need to know the energies of each of these particles. Now, each of the particles has energy associated with the fact that it exists, right? All of these particles have mass. And so there's a corresponding energy associated with that mass that we can calculate just with E equals mc squared. The other energy that these particles might have is kinetic energy, right? So we're going to have to consider their rest mass energy, the E equals mc squared, but we're also going to have to consider the fact that they might have kinetic energy. So we're told in this example that we've got an interaction that can occur. It's between something called a sigma plus particle and a proton and a neutral pion. And we're asked what the energies of the products are, assuming that the sigma plus particle was initially at rest. So Initially, if we're saying it's at rest, the sigma plus particle has no kinetic energy. So the total energy that we have to play with is just the E equals mc squared associated with the sigma plus. And all of that energy has to be converted into the rest mass energy of the two products, and the rest of it has to go somewhere, can't be created or destroyed. It has to go into the kinetic energy of those particles. Now, the way that we're going to do this is we're going to look at how much energy we would have before and after, and that's going to give us the total amount of energy and the total amount that goes into kinetic energy. To then figure out how much goes into one particle versus the other, you've got to use this slightly complicated formula in the second yellow box. This comes from the fact that once particles are moving kind of quickly, which these subatomic particles usually do, we need to use a slightly more complicated relationship between momentum and kinetic energy than what you have when you're kind of considering things that move slowly. So we've got to consider relativistic effects, and we're going to use that equation in the yellow box there. But let's kind of start off with the kind of easier step first. We're going to just figure out what the rest mass energies of all the particles are and use that to see how much is left over to give to the proton or the pion as kinetic energy. And in order to do that, we're going to need to know what the rest masses of our three particles are. And here is just a piece of the cutout of that table with the corresponding bits that we're going to need highlighted with these numbers. Right, so I'm going to have a go at switching over and working through that over here. I'd like to zoom in. Right, so what do? We consider the total energy before and after this decay. So we've got sigma plus, and then we might have some kinetic energy before, in general, which we'll represent by a Q for now, but that is 0, because we're told that the sigma plus particle is initially at rest, so the initial kinetic energy is 0. And this is going to, we're told that this is going to decay into a proton and a neutral pion. And then we're going to potentially have some additional energy. So this here is supposed to represent the kinetic energy of the products of that, the total kinetic energy of the proton and the neutral pion. Right, so how do we figure out the energy associated with the existence of this sigma plus particle? Well, it's just m of the sigma plus times c squared. And this has to be converted into the mass of the proton times c squared plus the mass of the pion times c squared. And then anything that's left over will go into that kinetic energy. Oops. Right, so the sigma plus particle, if we look down at the bottom here, the rest mass in units of MeV divided by c squared is 1189.4, if you can see this slightly. It's not very good resolution here. So we've got 1189.4 MeV over c squared for m. So this thing here is 1189 MeV over c squared. But then we're multiplying it by the c squared, right? So the c squareds just cancel out, and this one just becomes 1189. What was it? 0.4. 0.4. So now we see why maybe this is quite useful to use these kind of weird units of rest mass, because if we then want to convert it to an energy, we just basically cancel out those c squared factors. So we do the same for the other particles. The mass of the proton is 938.3 MeV over c squared. And when we multiply with the c squareds, they disappear, and we just get the 938.3, and this is all in MeV, of course, plus the 135.0 for the pion over here, plus Q, and I guess we should give ourselves a little note that the units that we're using here are mega electron volts for the energy. Right, so what do we need then for conservation of energy? We know that we can't create or destroy energy. The energy before and after has to be the same. So therefore, we need the Q to be 1189.4 minus those other two numbers, 938 plus 0.3 plus 135.0. And we'll get 116.1 MeV as the total energy that's left over. So in most of the examples that we're going to do, that you're going to be asked to calculate, actually that's as far as we're going to go. We're only going to be looking at figuring out what the total energy of the products has to be. Now you can go on, and that's done in the second step here. You can go on and figure out what proportion of the energy has to go into each of the different particles by using the fact that momentum has to be conserved as well. That means that because the sigma particle starts at rest, the proton and the pion have to have equal and opposite momentum, right? The total momentum before and afterwards has to be 0. So by using the fact that their momenta are equal and opposite, and by using this relationship in the second yellow box that relates the momentum to the kinetic energy, we can figure out how that 116 is shared between the two particles. Now, there's quite a bit of algebra there, and we don't have time to go through it there. Here you can obviously give it a go if you want to. And what happens, what you come out with is to see that the kinetic energy of the proton gets 19 of the MeVs, and the pion gets 97. But mostly, like I say, we're going to be just stopping at that first kind of step there. Right, and we have one last Kahoot question. Right, ready? Which of the following properties is not conserved in certain particle physics experiments? Some of them are always conserved, one of them is not always conserved. Okay, great. So yes, strangeness is not always conserved. So the moment of truth. Let's see who's on the podium. All right, well done to our 3 podium sitters. So that is us done, I think. Yes, so that's us done. We've got one more lecture on particle physics tomorrow morning. And yeah, the only other thing is obviously to have a look at the announcements on Canvas. Make sure you're ready for the labs in terms of getting the lab book and the and doing the safety induction. And happy to kind of take questions now if anybody's got any questions. See ya. Cheers. See ya. Hi. Yeah, it's what I can't remember what number it is, but there's a chapter on what's it called? It's one of the chapters towards the end of the textbook, possibly even one of the last ones. Yeah, should be able to. Can we see this? Might be able to see this quickly here. Contents, can we see this here? Right. That's the one. Can we see table of contents? Okay. Anyway, yeah, if you go and look in we don't seem to see the table of contents there. It's at the end. The only other thing is, this one topic is not covered in that much detail in this textbook, but there's another textbook in the library by Giancoli, Giancoli, and that one has much more detail on, it has a dedicated chapter for particle physics, again, towards the end. It has a similar name, Introductory Physics or something like that. So you have to go on and the easiest thing is to get it to print out. There is a PDF online that you can try and print if you want, but it's like 200 pages or something like that. So there's a link to the print store. You just click an order and it's $15 or something like that. And then you go and pick it up at the Union, at the Shortland building. Okay. But there's information on Canvas about that. Okay. Yep, no problem. Hi.
So the question is the rest mass should be memorize the value or it will be given in the question.
Sorry, say again?
So the value of the rest mass
Yeah.
of the antiparticles.
Yeah.
Should we learn the value or it will be given?
It will always be given. You'll always be given one of these. Oh, I don't have it. don't have one of these tables printed out here. Something. Yeah. So I mean, you'll always be given this, and for example, in the exam, this is, this table will be given in the kind of formula sheet. So you don't have to know any of these values for the particles.
Should you remember what comes from the decay?
No. So I mean, again, you'll always be given you'll always be told, okay, here's a possible decay. See, can it happen or not? So you don't have to remember, which ones can or can't. You just have to remember the kind of, which ideas do I have to use to figure out whether it can or can't happen. So you don't have to remember the details of what any of the answers are. Just just how you would go about figuring it out using these conservation rules. Yeah. Okay, no problem. Yeah. Hi.
I'm just wondering what the laboratories are going to be like. I have a vision.
Alex. Yeah. So, happy to. Okay, there's people coming in here after us, so if we just. I know, it's only Mick, it doesn't matter. Right, we'll go. 12:10. Yeah.
Nice. Back to back.
Yeah. Right. Well, if we just go out here, we can. Oh, sorry. Yeah, thanks. Well spotted. I just walk out with the microphones.